Hello, welcome back to Earth Science. In this lesson, we're going to be learning about the characteristics of igneous rocks. So we're continuing with geology. We did minerals, and now we jump to rocks, which are aggregates of minerals. Now there are four ways in which minerals form: crystallization from magma, precipitation, hydrothermal solution, and heat and pressure. The igneous rocks contain minerals formed exclusively through the crystallization from magma, or I guess technically lava. So igneous rocks form below the surface. Most of them form below the surface, but they also form on the surface of our planet. Intrusive igneous rocks, which are also called plutonic igneous rocks, these form from magma. Magma is any molten part of the geosphere that is below the surface of the geosphere. And intrusive igneous rocks will be they'll have the elements silicon and oxygen are typically the most common. Those are the most common elements on the surface of the geosphere anyways. But the deeper you go, the less and less silicate minerals become common. And then we get elements and mineral compounds rich with aluminum and iron, heavier elements. Because of differentiation, we find heavier elements in higher concentration the deeper in the geosphere we go. So this is Devil's Tower. It was the first ever national monument, at least in the United States. It was the first national monument. And it's an intrusive igneous rock body called a laccolith. Igneous rock formations can be highly distinct because sometimes they form these vertical columns, which are called joints, and they're hexagonal. The joints on Devil's Tower are huge. I've been there before. They're massive. They're like the size of redwood trees in terms of width, but they're much, much, much taller. Igneous rocks, intrusive igneous, well, any kind of igneous rock, minerals that form from crystallization from molten material are typically much harder if they form under the right conditions. So Devil's Tower really sticks out over the Wyoming landscape because all the other weaker sedimentary rocks have been weathered and eroded away. But this intrusive igneous rock body, which was once buried, all of the surface got eroded and exposed away, and then this beautiful, beautiful little iconic piece of American Midwest, I guess, is there for us to see and to be able to interpret. So knowing that that formed deep below the ground millions of years ago from a magma chamber makes it even more interesting to look at rather than just seeing it, I suppose. The extrusive igneous rocks form from lava. So when the molten material comes to the surface, then we call it lava. But that's really the only difference between lava and magma. Now, underwater is still the surface because we mean the surface of the geosphere. We're studying geology right now. So underwater is technically the surface of the geosphere. So it means the same thing. In Siberia, there's a huge region called the Siberian Traps where a very long time ago, like 250 million years ago or so, what's called a fissure eruption happened. And this is where a continent basically is torn apart lengthwise. And so rather than an isolated volcano, you get a massive crack that can go for hundreds, maybe thousands of kilometers, and lava just erupts to the surface. Fissure eruptions are bad, bad, bad news for the climate and for life. This was a major contributing factor to one of the largest extinction, well, the largest extinction, most likely, on our planet, at least in terms of complex multicellular life. It was the worst ever extinction called the Permian extinction. And here's an example of, so this the dark color and the fact that we don't see really layers like we do with sedimentary rock formations tells us, or is a clue, that this is an igneous rock formation. But just look at the depth of it. Imagine, here's a lava field in Hawaii. And yeah, it's extensive. It covers a very large area and it's fairly deep, but it's nothing on the scale of these formations in Siberia. And we think that fissure eruption basically continued for a period of around 1 million years. Not good. Very much not good. These are what are called pillow lavas. So here's an example of extrusive igneous rock that is formed below the water on the surface of the geosphere. So I encourage you to look up videos of pillow lava being formed. It's a really cool, sort of mesmerizing thing to watch it. The lava expands, but then it crystallizes on the surface because of the water. The water absorbs heat very well. So it's interesting to watch pillow lavas grow. And then here are some pillow lavas that erupted who knows how long ago, and they're on the surface today for us to look at. Now, the way we classify igneous rocks is based on their texture and their composition. The texture is actually really easy to, it's pretty easy to see, and it tells you whether or not the rock is intrusive or extrusive. So you can, with certain igneous rocks, you can see the individual minerals that they're composed of. Whereas composition really refers to how much silica is present in the igneous rock. That's the most common group of minerals on the surface. But as I said, with igneous rocks, most of them form deep below the surface. So we get lots of variation in how much silicate is present. And usually feldspar and quartz those are the most common silica minerals. So the texture of the igneous rock tells you how long the igneous rock spent crystallizing. So coarse-grained igneous rocks, these are the result of slow cooling that allow large crystals to grow. Now, large can mean even just a millimeter wide is considered large because it's different for different minerals. But it can take hundreds of years for a quartz crystal to grow to be a few millimeters wide, for example. The fine-grained texture, this is where, they're not going to be smooth like a countertop is or something that's polished, but there's a really easily noticeable difference in texture between fine-grained and coarse-grained. So fine-grained igneous rocks are extrusive. They form on the surface. So coarse-grained form from magma below the surface. Fine-grained igneous rocks form on the surface from lava. But there's more to it than that. Some igneous rocks can go beyond being fine and have a glassy texture. They literally are glass. In fact, obsidian is the best known example. So these are always extrusive igneous rocks that crystallize very quickly. Now, you have to have the right kind of minerals present. Obsidian, for example, is almost completely made of quartz. If you have different kinds of minerals present, not all minerals crystallize in a glassy way like silica does. So it also depends on the type of minerals that are present. And some glassy textures actually get full of holes and they produce bubbles. We call that vesicular. But there are also fine-grained igneous rocks that are vesicular as well. They're full of holes, as it says there. The final texture, which is a really bizarre one, is porphyritic. So in the coarse-grained igneous rocks, the minerals are fairly large, they're easy to see, but they're usually very consistent. The difference in size between the different minerals is fairly uniform, but porphyritic igneous rocks, they have minerals of very different sizes. Now typically this happens because an igneous rock, or a magma body I should say, can spend thousands of years cooling down. Now, different minerals crystallize at different temperatures. So let's say our magma body starts at a temperature of around 1,000 degrees Celsius, and it has some minerals that do start crystallizing at around, let's just say 800 degrees Celsius. Well, for hundreds and hundreds of years, the rock cools from 1,000, then down to 800, then down to, let's just say 300 degrees Celsius. And at that temperature, other minerals, whose raw ingredients are always there, but they can't start crystallizing until the temperature cools down. So as the rock continues to cool, those other minerals that crystallize at higher temperature have a big head start. And so they've been growing and crystallizing for centuries ahead of the other ones. So porphyritic igneous rocks have an inconsistent texture. And I'll show you what that looks like. So here's coarse-grained igneous rocks. Not really too exciting, but there they are. We can see the dark and the light and the chalky and the glassy colored minerals all separate from each other on these. So that tells you it formed underground. This is rhyolite. So again, it's not smooth like glass or anything like that, but this is fine-grained. if we look at this closely, we can't really actually see the individual mineral grains. We'd have to have a magnifier in order to actually see them. So it's smooth, it's just not glassy. But obsidian, like we said, this is definitely, it literally is glass. So it's got that extremely smooth texture. The minerals just simply, I mean, they almost don't crystallize in any sense. They're so fine that there's just no detecting any crystals there. It's more just like a single homogeneous body. And this is vesicular basalt. So it's full of those holes. Pumice is actually glass. Now I have a lab video later on in this playlist for you to check out where I have some pumice, and it's full of holes too, but it's actually glass. And so it crunches when you try to break it with your fingernail, and it floats in water. And here's a porphyritic rock. So the black matrix is made of much finer grained minerals. Not really sure what they are exactly. But then these other lighter colored minerals have grown to very large sizes. Now, the use in this information is it helps us interpret the geology of our surroundings. So this is Yosemite National Park. It's pretty close to where I live. And if we look at the rock bodies all around, we notice that there really aren't layers to them. It's all sort of a uniform, single body of rock. Now, it's been eroded and weathered away through glaciers and running water and all kinds of other things. But really, it's one continuous, massive rock formation, in a sense. And it's made of igneous rock. The fact that there's no layers helps us determine that. But if we could look at this even more closely, we would see that all of the rocks in Yosemite are made of granite. Now, granite is an intrusive igneous rock. It's coarse-grained. So we know, because of that this entire landscape, the rocks that make up the body of all this wonderful landscape, well, they formed deep within the earth an extremely long time ago. And this unbelievably large body of granite crystallized and solidified and hardened underground long time ago. Plate tectonics, as it lifted up the Rocky Mountains and basically the entire western half of North America, which is fairly mountainous, it lifted that intrusive granite up closer towards the surface. And then erosion took away the top layers, like what we saw in Devil's Tower. And then over millions and millions of years, ice and flowing water, we can see a waterfall in here, sculpted away a lot of it, but much of it is still there for us to take a look at. Now, moving on to composition, the minerals that we find in igneous rocks, they determine their composition, and to a certain extent, color can be, and by really color we mean lightness or darkness, is a pretty good indicator of the composition, but not in 100% of the cases. So felsic, otherwise known as granitic composition igneous rocks, they have the lightest composition typically, although I'll tell you what I mean. What makes felsic igneous rocks the way they are is they contain the highest percentage, greater than 63% silica. Now, sometimes there will be dark minerals present, but silica, like quartz, doesn't have to be a transparent mineral. It usually is. It has a vitreous luster, so even if it has some color, it's still fairly transparent. But obsidian, for example, is like basically the most felsic igneous rock there is. It's almost 100% silica, but it's almost always jet black. You really can't see through it. Normally, in most cases, the lightness is also an indicator of its composition, but technically, we're really just measuring what's its composition in terms of percentage of silica. The basaltic composition, there are different words for these, but these are the ones I'm going to use. It's called basaltic because basalt is a very common rock with this composition, and they contain between 52 to 62% silica, and they'll be usually heavier in magnesium and iron elements as well. The andesite is a rock that fits between here. These are darker than the granitic igneous rocks, but lighter than the basaltic typically. I realized I had my percentages backwards, but I just fixed them. So it's the basaltic rocks where the silica content is between 45 and 52%. The andesitic igneous rocks, their silica content is greater than basaltic, less than felsic or igneous. So my mistake. And then finally, there are the ultramafic igneous rocks. Now these typically are very dark. Sometimes they're green though in color. And olivine is a green mineral, and they tend to be common in these ultramafic rocks, so that's why they can be green. And they are composed of less than 45% silica. So by comparison, they have the least amount of silica, and ultramafic rocks are always intrusive as well. So here's just a close-up of some granite, of felsic igneous rock. Yes, there are dark minerals present, but for the most part, light in composition. Here's some andesite for you to look at. Here's some basalt. It's a little bit darker. And then this is olivine right here. In this case, they're actually green. So that does it for the igneous rocks. Next time we'll be studying sedimentary rocks. Thanks for watching.